Get started. My name's Damon Kohler. I'm a software engineer at Google, and wanted to talk to you guys about cloud robotics. Just a little bit about me. I live and work in Munich. I've been at Google for a little over 6 years now. Just a couple of my open source projects that I've worked on are rosjava, which we'll talk about a lot today, and a scripting layer for Android. So the talk, I'm going to just go over what cloud robotics is, or the concepts. The talk will actually be a lot more focused on ROS on Android, and I'll leave you all with a few areas for development in cloud robotics. So in the talk, there'll be a lot of high-level stuff about ROS and about cloud robotics. There's going to be some code, and there should be lots of cool robot videos. All right, so the big problem with robots is that they're really hard. There's a lot of things that make them hard. Some of the things are the limited resources that are available to them. I don't know if anybody attended the talk yesterday about robots that care, but I think a lot of this stuff was mentioned. Limited resources, closed platforms, really broad scope. It takes a lot of knowledge to actually build a working robot and make it do something useful. And all of that scope leads to a lot of complex code. And all of this together leads to a lot of frustrated developers. So I think all of these things lead to the slow pace of robotics research and development these days. So I think the solution's actually pretty obvious. We should make robots a lot easier. And most of these things we can do in pretty straightforward ways. We can offer unlimited resources. We can make all of the platforms open, easier for developers to look inside and figure out how things are working when things don't go right, which happens all the time. We can also limit the scope, so developers don't have to know everything about a robot to make a robot do something new and exciting. And all of this together will help simplify the code and lead to much happier developers. So robot operating system, also known as ROS, is not an operating system, not at all. Actually, it's kind of a pub-sub framework, and probably in a much larger way, it's a community. So the pub-sub framework is multi-platform, multi-language, runs on all of your favorite languages. It's open source, completely open source, BSD, so it's very friendly license. It's extremely popular in academia right now. It was actually developed, it's maintained by Willow Garage. I think it was originally developed at Stanford for the DARPA Grand Challenge. Willow Garage is a small startup robotics company in Silicon Valley. So what does it do? Well, in the video here, the video is a couple years old. ROS is about 5 years old right now. But this was the 3-year anniversary for ROS. And we'll see a few robots, actually, that are running ROS, doing all sorts of different tasks, cooking and navigating, giving high fives. So ROS does lots and lots of things. Because of the way it's designed, they're able to offer all sorts of different drivers for sensors and motors and actuators, things like that, algorithms that actually drive all these things in intelligent ways. Visualization tools like you see right now. This is actually called RViz, which is sort of a generic visualization tool for your robots that is provided by ROS. Maybe you've seen some of these videos on YouTube before. I think a lot of them are relatively famous. There's simulation, so both in 2D and 3D. We'll look at some of that today. Diagnostic tools, debugging, logging, and testing. Everything you need to actually build and maintain a really complex system. Which is what robots are. They're hugely complex systems, although typically they're all sort of packed into that actual physical device itself. So the simple act of, this is the PR2, by the way, that you just saw from, which is actually Willow Garage's robot. But the simple act of actually opening a door like that or pulling open a refrigerator, depending on the robot, that can have varying levels of complexity. So the PR2, for example, has to do quite a lot of maneuvering. And you'll see these towel folding videos are running at 20x, 30x sometimes. So they've got a long way to go, despite all the very cool things that they're already doing. ROS is great because it also runs on lots of really commodity hardware like Legos, the iRobot Create, maybe you're familiar with that. So you can run ROS on your Roomba, there's one. The Now that everybody probably saw while they were here also has ROS drivers. And it's also used on cars. Like I said, it was originally developed actually for the DARPA Grand Challenge. So a more recent challenge, not the grand challenge, but the robotics challenge that was pretty recently announced by DARPA, is to actually create these humanoid robots to go and do search and rescue operations, firefighting, crazy things like that. And so you see this like ninja-like robot climbing over all kinds of things that I think it's actually a little bit frightening to watch. It's very Terminator-esque. And it was actually developed by Boston Dynamics. This is the Atlas prototype. There's also Petman, which I think either led to this or something. I'm not quite sure about the history exactly there. But the OSRF, the Open Source Robotics Foundation, is actually a spin-off of Willow Garage. And they've been contracted with DARPA to actually develop the simulator for the robotics challenge. So the 3D simulator that is shipped with ROS called Gazebo will actually be simulating this super awesome humanoid robot in the near future. Another robot you may have heard about is Robonaut 2, or just Robonaut most of the time. So it actually lives and works on the ISS. It's a very complex, pretty awesome robot, does all kinds of crazy things. It's also available in simulation on Gazebo, so you can have your very own robot astronaut in your, running on your laptop. Here you see actually it's going through using, they call it the task panel. And basically, they're trying to design this robot so that it can automate some very mundane tasks that astronauts do. I've actually learned a lot about what astronauts do recently, and they spend a lot of time doing things that aren't that exciting, actually. Other than being in space while they're doing it, they need to push a lot of buttons and measure a lot of things every day that a robot could actually help them a lot. And their time is very valuable. So having a robot on the ISS could actually be, could have a significant impact on the sorts of things we're able to do up there. And as you can see, it's actually a pretty impressive robot, 42 degrees of freedom, and it's only from the waist up. Right, so there's a lot going on there. All right. So these are all pretty cool, but what makes ROS really useful? And once again, I think the answer for that is that robots are very hard. There's the scope involved in being able to actually create something like the Robonaut is massive. And you can't expect you or your company to actually put all of that together by themselves. That's that you're wasting a lot of time. You're not building off of all these things that all these universities and other research and development communities have been putting into their robots themselves. And so ROS was created in order to actually promote code reuse in the robotics community. Willow Garage believes that robots in every home is something that will happen, but it's not happening fast enough for their liking. So they focused on actually how can we create a community, create some software and everything that will drive this whole revolution forward faster. So now I'll talk a little bit about actually how ROS is set up to make that happen. So the whole goal, remember, is code reuse. So in ROS, each reusable chunk of code is called a node. These are functional components like a laser scanner. Usually something like RViz, the visualization tool, will be made up of lots of different nodes that are working together to accomplish a task, which is actually how you would think of a robot. All of these nodes coming together to make a graph that accomplish something really complex. Each node is usually a process. There are nodes that are threads, but it's helpful to think of them as processes to start with. They're compiled and executed individually, and they're named. So you create a graph of all these nodes, which we would have a laser scanner talking to something that would visualize the laser scan, for example. But then they need to actually communicate this information between them. And so the way they do that is with message passing. So ROS messages are exchanged between nodes. They're strictly typed data structures defined by an IDL. The IDL actually was created, well, ROS was open source just before Google actually open sourced protobuf. So if things had turned out slightly differently, ROS might be using protobuf. But as it is, they're using their own IDL for defining these messages. So you would have something, a little text file that has things like float64 array of ranges for a laser scan. So that might contain the different ranges that were returned from a single sweep of a laser scan. And then every message has a name. So the sensor messages is a package, and the laser scan would be the actual message name. So then we just have to figure out how to exchange these messages. So in ROS, messages are exchanged via topics and services primarily. So topics are the broadcast mechanism. So it's a many-to-many pub sub, right? So you can have lots of different publishers for a particular name topic, and you can have lots of different subscribers for that topic. And everything that's published to that topic is visible to all the subscribers of that topic. So each topic is also named, similarly to the way the nodes are named. They use these Linux file path name style names. And then it's also typed with the type of message that's going to come across. So the scan topic might contain laser scan messages. And then services are Ross's version of RPC. So these are synchronous one-to-one topics. So rather than simply having one type, they have a request and a response type. So in summary, it kind of looks like this. This would be a very simple ROS graph. You have two nodes. One is actually publishing information. Let's say it's a laser scanner driver. And the other one is subscribing to these things. It could be visualizing those laser scans. And then maybe there is some sort of RPC that would be useful in that case. So I say, or I hypothesize, that this is actually the reason that ROS has been so successful. The way that they've been able to actually promote code reuse is that these cohesive components they call nodes, and this message passing architecture creates these reusable code nuggets, right? So message passing is a great way to ensure that, or to help promote functional components that do not leak, so that they're more easily reused by others. You create really well-defined APIs that are using these strictly typed messages, and you shift them back and forth. And now you've created, the community has created things like laser scan messages. So when I want to do something new with a laser scan or write a driver for a new laser scanner, everybody can be pretty, can rest assured that they will actually be able to make use of my code. The other really great thing about this is that it avoids license contamination. So ROS is also very interested in making sure that these platforms stay open, because open platforms are really important to a healthy developer environment. And since all of these nodes are compiled and executed separately and communicate over the network, for example, then they're isolated from each other. All right, so one example of something ROS provides is navigation. And I said robots are very complex, so this is one of my examples of a particular way that they're complex. So this is the PR2 actually driving around the Willow Garage office, and you see RViz showing the 3D point clouds and the cost maps for all the different things that it needs to figure out while it's navigating so that it doesn't run into stuff. So it can figure out where it is. It's building a map right now using something called SLAM, simultaneous localization and mapping. And you can see it can see very small obstacles, and it's moving pretty quickly and sort of slaloming through these things. So it has to do lots of different stuff to make this happen. Creating the map, like I said, and localization, so that's the SLAM part. Figuring out a path to go from A to B, and avoiding obstacles like this guy, and driving those laser scanners. So something has to actually read those laser scanners and give it to the rest of the system so that it can make smart decisions about it. Then it actually has to go and control the motors to do the right things after it's made those decisions. And then you also have to be able to talk to the user to figure out, okay, well, where is it that they want the robot to go? Okay, so this is a ROS graph, which I sort of mentioned a few times. You can look at all the squares and the circles as nodes, and all of the edges are actually topics or services. So in this is sort of a higher level version of this. Navigation is actually made up of a few more nodes. Some of these nodes that are in here are groups of nodes, really. But the map server offers a service on the name/map, and then the global cost map can actually query the map server and get a map. And in this case, the map is usually an occupancy grid, which is a grid that represents the world, and every cell in the grid is the probability of that space being occupied. So lots and lots of robots these days are based on heuristics, probabilistic robotics, they call it. In this particular case, the probabilities are used to compute how the cost of making the robot go from, say, the living room to the dining room. Then below that, we see the local cost map, which is sort of a cost of the what's around the robot in the immediate vicinity of the robot. So we've looked at how much it's going to cost to go from A to B over some long distance, and now we need to figure out how much it's going to cost to go around that person that just fell in front of me or go over them. The recovery behaviors are things that happen when stuff goes wrong, because things are always going wrong. And the idea there is to, the cost map perhaps is incorrect. It's missing some information, or it's got, it didn't see that person that fell in front of it got up and walked away, things like that. And so the recovery behaviors go and try to update those cost maps. So when the robot thinks it's stuck and it can't do anything safely, it falls into these recovery behaviors and tries to figure out what to do next. So then from both of those cost maps, we actually have the global planner and the local planner. So those things actually come up with a trajectory for how the robot should move to accomplish its next goal, right? Next sub-goal on the way to its primary goal, which would be the thing that the user told it to do. So if I told the robot to drive from the center of the living room to the center of the dining room, it would plan a path according to the global cost map that would take it there as efficiently as possible. And then it would plan a local path that would actually move the robot onto that global path as efficiently as possible. So that's why you actually see the local planner publishing to the CMD-vel topic, which is a common topic for these twist messages, to something called the base controller. The base controller in this case is the thing that's actually responsible for figuring out from that twist message, which is a combination of linear and angular velocity, how the motor should be driven in such a way so that the robot will follow that path. On the left-hand side, you actually see some additional sensor sources. So odometry is pretty frequently used. This is something that says that monitors how far wheels have turned and in which direction. So it's sort of a dead reckoning type system to figure out where a robot has been. And then in addition, there's the TF stuff, which is actually, unfortunately, outside the scope of this talk, but is a very important piece of ROS. TF is what is used to maintain and transform between different frames of reference and the robot, so that it's able to have a laser scanner on its head and move its arm around and know where the points are that that laser scanner is returning relative to like the hand or something, so that it doesn't collide, so it can plan how to move its arm. Okay, so I think that's relatively complex, and it takes a hell of a robot to do it, and it's not cheap. So if you saw the robots that Care yesterday, there were some other even more expensive robots. But the PR2 is $400,000 plus tax and shipping. If you are a proven contributor to open source, they'll actually give you a discount, and they'll give it to you for $250, I think. In the base are two 8-core i7 servers, 24 gigs of RAM apiece, massive servers. Everybody that I talk to that works on the PR2 says that whenever they actually are doing a demo, say at TU München, when they do cooking pancakes or making popcorn or something like that, all the cores are pegged all the time. So they don't actually have enough resources to do everything they want to do, and they're constantly making compromises. On the robot, in terms of sensors, there's 7 cameras, 4 of which are stereo pairs. Stereo cameras, in case you don't know, actually can provide depth information. 2 laser rangefinders, so they're actually the same laser rangefinder. One is in the base, and that's typically used for building maps, figuring out, localizing, figuring out where the robot is. And then a tilting one that you see actually just below the head, and that provides some 3D information. And then both of the arms are actually really interesting on the PR2 because the PR2 is designed to be sort of a personal robot, right? It's supposed to work among humans. And so the arms are actually compliant. They're driven with a belt system. So that means that if you were to arm wrestle the PR2, you would win every time. It's very easy to overpower. I think it can, I forgot exactly how much it can lift, but when they go to like open a refrigerator or something like that, they actually have to move the base of the PR2 because the base has so much more power, and the gripper is stronger enough so that it can hold on to the refrigerator, so they can just sort of drag the refrigerator door open, but the arm itself is not powerful enough to do that. The base is omnidirectional, which makes navigation, path planning a lot easier. And the whole idea of the PR2 actually mirrors the whole idea of ROS, which is they wanted to create a robot that would allow roboticists to specialize on a particular area. So they wouldn't have to figure out all of this stuff, how to wire and build this robot so that it would be robust and work on a day-to-day basis. And instead, they can just focus on one piece, like motion planning for the arm, or figuring out the best way to pick up a coffee cup. Okay. So navigation is really hard. It takes a really expensive robot to do it. Let's look at something much simpler, like the right-hand rule. So if you don't know the right-hand rule, essentially it is a way to solve a maze. You put your right hand on the wall next to you, and you walk. And as long as you keep your right hand on the wall, you will eventually find your way out of the maze, assuming the maze meets some qualifications. Simple mazes. All right, but to do that, I'm going to actually show some code. So first I want to tell you a little bit about rosjava, which is the Java client library for ROS. I started developing it 2 years ago together with Willow Garage. It's Android compatible, and it's open source, and you can go try it now. So rosjava, unlike some ROS client libraries, is pretty much entirely an asynchronous API. So it takes message listeners, node listeners, so there's lifecycle events, things like that. And the entire thing's built on Netty for the networking part. The reason I decided to do this is because asynchronous APIs can actually achieve better performance typically than the synchronous ones, and also much the same way that I think messages and this pub subsystem in ROS help promote good coupling and cohesion. I think asynchronous APIs do the same thing. rosjava projects are built with Gradle. So most ROS projects are actually built with CMake, but that didn't really fit the Java world very well, so we switched to Gradle. On the right is sort of an example Gradle build script for a rosjava project. Gradle is a very flexible build by convention tool. It's compatible with Maven and Ant. It's been really good to me so far. Yeah, and it's pretty straightforward. So on the right, we just have you have a Java plugin. So Gradle can actually build projects in other languages as well. You specify your dependencies in terms of artifact IDs, which probably look familiar to most of you. And it can pull these artifacts from Maven repositories natively. Okay, so in rosjava, the concept of a node is typically implemented in terms of a NodeMain. And a NodeMain is just an interface that is actually just gives you sort of the lifecycle listener methods. And just like a NodeMain has a node name. And in this case, all of those graph names, those Linux file path looking names are wrapped in graph name objects in rosjava. So we return one of these graph names, and we'll call this node the right-hand rule node, because that's what it does. And then when we start up the node, then the onStart method will be called. So in onStart, we're actually handed something called a connected node. And that connected node is sort of a factory and a way for us to talk to the rest of the ROS graph. So from that thing, we'll be able to create our publishers and our subscribers. There's lots of other things that are parts of ROS that I haven't gone into in this talk and won't be able to. And those are pretty much entirely provided to you through this connected node object. So when we want to create a publisher, we ask the connected node to create a new publisher. We tell it the topic, so the cmd-val topic we'll use again. And we're going to use the geometry messages twist message, like I showed you before. So we create one of those new messages, and then we'll publish it later after we fill it in with some interesting stuff. Then we create a subscriber. So this is a pretty simple robot. It's only going to use the laser scanner and publish these twist messages. And actually, all the other stuff has already been done for us. Like I said, we're reusing things, right? We don't. I mean, this robot's only running in simulation, but the simulation already knows how to take a twist message and actually move the robot around. I mean, we didn't have to do any of that. So the subscriber takes a laser scanner, which the simulation knows how to provide, and we subscribe to something called base scan. Base scan is the name of the topic that the PR2 uses for its lower laser scan. So this is kind of a common one to use. And so we take those laser scan messages. So for the subscriber, then we just need to add a message listener. And this message listener will be called every time we get a new laser scan message from the laser scanner. And then it'll call on new message, we get the message, and then we get to actually do our business logic, right? So this is where we're solving the right-hand rule and reacting to the incoming messages from the laser scanner. So the laser scanner, in case you're not familiar with laser scanners, essentially the 2D ones at least provide you a plane of information. So they sweep in an arc, and then every n degrees, they actually give you the range to the obstacle from the laser scanner. All this information is actually encoded into the laser scan message. It tells you the angular resolution, the maximum range, the minimum range, all kinds of things like that. So you can do lots of math and figure out exactly what it is you're looking at. In this case, though, it's in simulation. It's all pretty straightforward, so we're going to take a very simplistic look at it. And we're going to say, OK, the range directly in front of me is the middle point in this list of ranges returned from the laser scanner. And then I'm going to look a little bit to the right, about 30 degrees or so, and look at that range as well. All right, so this is telling me, am I going to run into something here, and how close am I to the wall, or how close will I be to the wall soon? So then we set some default linear and angular velocity. In this case, these units are in meters per second and radians per second. And so we're going to move forward at 50 centimeters a second, and we're going to sort of turn to the right a little bit at 0.5 radians per second. And then when we look at the laser scanner, the ranges that we extracted, then we can sort of see whether or not we're within 1 meter of the wall in front of us, and I don't know, I'm not going to do the trig in my head, relatively close to the wall to the right. And if we are, then we want to change those default linear and angular velocities. So we want to stop moving forward so that we don't run into anything, and we want to turn away from the wall for a little while until it's far enough away. Then we just set those parameters on the twist message that we created earlier with the publisher, and then we publish it. And the rest is taken care of for us. So this is the stage simulator, which is the 2D simulator in ROS. And you can see the little bluish black dot up there running around, following the right-hand wall. This is actually in real time. 50 centimeters per second is pretty fast. I wouldn't want to be next to a robot doing that, actually. But yes, so it just zips around, trying to follow the right-hand wall. This is just a maze that I found online, a little web maze generator. And there it goes. And it's out. And actually, my favorite part about this simulation is that it follows the wall all the way back around. And it starts over again. That was totally by accident, but pretty amazing. OK. So great. Navigation, right-hand rule. Why don't all robots do this? Well, because the world is not a maze that meets certain qualifications. So, why are we talking about the cloud? So I haven't said too much about the cloud yet. I think this graph is pretty good evidence for why the cloud would be useful in the robotics world. So the PR2 has about 2 hours of battery life. And you might expect that all of this battery power is going into the motors or into the arms and all these other things. These things actually have to move mass, right? That should take lots of power. Turns out that it takes way more power just to do the computation. If you turn off one of the servers in the PR2, you double the battery life. So I think this kind of points to a well-known software concept, separation of concerns. And I'm just sort of reapplying that to robotics in this case, or cloud robotics. The idea is that if I can reduce the amount of compute power that is required on the actual device itself, then I can move all of that compute power into the cloud. So while there are plenty of things that need to happen in real time on a robot, there are lots and lots of things that really don't need to happen in real time. And network connectivity getting better as it is, and low power CPUs improving as they are, this is totally feasible. So we would use the local CPU, and instead of for doing everything, we would actually just hook up to the sensors and hardware, right? We need something locally there to act as a driver and get all this information, and then take care of any real-time concerns like not punching you in the face or something, and then handle the connectivity as well, right? And then once we have connectivity and we have all of that, then we can move into the cloud and do all of the really heavy computing type stuff. And this. In addition to having all these unlimited resources in the cloud, essentially, and despite the latency and things like that, it turns out that when you talk to a lot of the robotics researchers and you ask them about the sorts of problems they have and the sorts of compromises they have to make due to the CPU resources that they have available on their robot, many of them would be happy to pay a latency price to have a better answer, right? And so if you can solve a very complex problem on a very large cluster, and just add network latency to whatever the compute time was, and give them a much better answer, they would be much happier. And another nice thing about actually moving all this stuff into the cloud is that these robots can then share information with each other. So let's say I had two PR2s, and they were trying to figure out their way around Willow Garage, maybe locate all of the plug outlets so that they can charge themselves. The PR2 actually does, or has, I think, for 3 weeks, ran around Willow Garage plugging itself in at night. Or well, every 2 hours, I guess. These robots could actually communicate through the cloud and build a map together, right? So that neither robot would have to see the entire office in order to build a representation of the entire office. And this is a pretty powerful concept. Right, so data centers, that's what the cloud is, right? They've got a lot of good things going for them. They're very power efficient, they're very powerful, they're very well connected. But you can't put one on a robot, it would be way too heavy, and they're super expensive. So they're a shared resource, but they're a very powerful shared resource. Mobile devices, on the other hand, make a great, very power efficient, cheap, local compute engine. Right? They're loaded with sensors already that we can make use of on our robots. They're very user-friendly. I mean, that's what they were designed for. And they're connected. Right? So they actually meet a lot of these requirements for what needs to be local on the robot. They've got plenty of compute power to handle many real-time concerns. And they keep getting faster and faster very rapidly. But they do have relatively little compute power, so you're not going to be able to right now build a PR2 that is running on your Android phone because it's just not powerful enough. And the other, I think, main problem is that it's been historically difficult to actually connect them to other hardware, right? They're very tightly integrated devices, and a robot is actually a big conglomeration of lots of different devices, and you need to be able to communicate with those and work with them. And so, how do you get past that barrier? And Android actually makes that pretty easy these days. In addition to devices that support USB host mode, so with USB host mode, you can plug in your laser scanner. The device can actually see it as a USB device. And then if you're using a Hokuyo, like down here in the corner, which is also the laser scanner that the PR2 uses, you can actually talk to it over a standard USB serial protocol called CDC-ACM. So I've done that before, and there's a ROS package called Android ACM serial, and you can actually read a laser scanner from your Android phone, which I think is pretty cool. Then on Android, there's also the Open Accessory API. And so Open Accessory is Android's way of allowing you to connect your Android phone to devices, hardware devices, and also receive power from them, right? So in this case, the 80K board, which was based on an Arduino or very similar to an Arduino, will actually provide power to the Android device and act as the USB host. Right? So that means that they can actually support lots of phones, whether or not they have the hardware inside them to support USB host mode or not. And then there is the Yo-Yo board, which actually also supports the Open Accessory API, and then another custom API over ADB, the Android debug bridge. So the Yo-Yo is also very popular and is another way to actually connect all this hardware together with your Android device. All right, so about 3 years ago, Cellbots.com showed up, and they started doing these sorts of things. All right, so this is actually a G1, which I think shows the age of the video very well. And he's using the speech recognition API in Android to actually drive the robot. Right? So he says, go forward, and the robot goes forward. And he says, go backwards, and the robot goes backwards. And then there's TTS and built-in sensors, right? So now he's using the compass sensor to actually ask the robot to orient itself towards the south. Right? I think he could use a little bit of extra tread on those wheels because it tends to do a lot of overshooting, but it gets there eventually. And then it tells him that, okay, I've accomplished my goal, right? It tells him with a computerized voice, right? This is a great way for robots to interact with us, right? And for us to interact with robots. When we can tell them what we want and they can tell us what they've got, or what they've done in return, then this is a very natural interaction. And that's 3 years old. Since then, 2 years ago, I started working on rosjava, and we announced it at Google I/O. And now rosjava is actually running all sorts of different things. So here you see the phone actually being, the compass on the phone being used to determine the orientation and display that. This robot is following lines using the camera from the phone. This is called the Turtlebot. I'll talk a little bit about it later. And it's being driven, teleoperated by an Android tablet. These two guys are being teleoperated together. So this is actually me using a laser scanner and an IMU and a ROS package known as HectorSlam to actually build a map and display that on the Android device just by walking around. So HectorSlam is a odometryless SLAM algorithm. And then this robot coming up here, so this is a teleoperation app that shows the map and allows you to tell the robot to go places. And this little robot's called Parsec. I'll tell you a little bit about more about him in a second. So Parsec is a mobile perception platform. And the only computation power on it is the Zoom tablet that you see at the top and an Arduino. So the tablet is actually responsible for talking to the position controllers, the motor controllers, the ultrasonics. It's got 3 laser scanners on board. And it's essentially the dumb terminal of the robot world, right? So this is like the cloud robotics test case. So this thing is able to drive around, build a map of its surroundings, navigate. You can point and click to tell it to go from one room to another. It can find its way there. It can avoid obstacles in 3D. So here you see it actually picking up that little solder reel on the floor. And the thing's actually driven with a hobby servo. So this robot is quite cheap, and it has a lot of similar capabilities to a really fancy research robot like the PR2. But at the same time, you can compensate a lot you can compensate a lot with hardware on robots. So the better the hardware, the better the results, which is kind of what the PR2 does. You're paying for really precise machinery, but you can also do the same thing in software, right? So what already exists? By using the cloud, we saw a robot actually be able to accept your commands via voice recognition. We saw it be able to navigate a space, right? Build a map on some off-board computer someplace, and figure out how to get from A to B. There's lots of other things that are already in existence that were built for us, for humans as consumers, to help us get around day to day. And robots can actually benefit from a lot of those things as well. So optical character recognition is actually a really important one, because when you think about it, the spaces that we navigate every day indoors don't have a lot of distinctive features in terms of what a laser scanner might look like, right? We can't figure out how to get from A to B without looking at a road sign or two ourselves. And so we can't really expect robots to operate in that world without being able to do the same thing. Text-to-speech we talked about, and translation is really important too, right? So not everybody speaks the same languages, and the robot needs to be able to communicate with everybody that it runs into. So translation is really important. But there's lots of things missing. And so we can get pretty far with a lot of the existing cloud services that were built for us and using them on the robots. And Android is a great way to get started with that. But robot problems usually fall into 3 categories: perception, mobility, and manipulation. And there's a lot of specific things that we as humans don't need, but robots really do. And we could put those into the cloud. So for example, figuring out the best way to pick up a cup, or figuring out that that is a cup, right? So when it wants to pick up a glass of water, we need to run a bunch of simulations to figure out the best way for a particular style of gripper to actually get a hold of that thing. And then when it picks it up, we also need to run a bunch of simulations to figure out what the best way is to put it back down. Glasses don't stand very well on their edge, for example. And having a service in the cloud like that, where you could say something like use Google Goggles to figure out that this is a particular coffee mug, and then we could go look up, okay, well, we ran a whole bunch of simulations on this before. We should pick it up this way. We should put it down this way. We can fill it from the top, but we can't fill it from the bottom. Things like that. Those are very important. Perception is a really hard problem, and this is one where that I've talked to a lot of people about, and they constantly run into issues because they have to make compromises about exactly how they're going to move forward with perception. Image recognition, image feature recognition is a pretty hard problem, and it takes a lot of CPU power to do it. So when you have to choose between 5 or 6 different image features, if you moved it into the cloud, you might not have to choose. You could just solve all of them simultaneously and get that result back, right? And then pick the best one, rather than having to choose one ahead of time based on your situation. And manipulation, and mobility, right? So when Parsec navigates around a space and it builds that map, it can put that map into the cloud, share that with other instances of Parsec. You can drive it over the internet really easily. You could say where you want to go, things like that. So all of these services don't exist yet. And that's what I'm hoping all of you might provide. So if you want to get started, There's lots of great tutorials about ROS. The documentation for ROS is really quite great, especially considering this is an open source project. I'm sure many of you are familiar with open source projects that are lacking significantly in documentation. But the tutorials for getting started with ROS are really pretty good, and we'll walk you through. The learning curve is a little bit steep, but the reward is really great because you get to reuse all of these really complicated things. You don't have to know what SLAM is in order to use one of these turtlebots with SLAM. So the turtlebot then is sort of a great platform. So once you've already experimented a bit with ROS and you like it and you've played with the simulator and now you want to actually have a robot in your home that's maybe doing something interesting. The turtlebot is a great way to do that because it's relatively cheap. It's a completely open source platform, and there's lots of accessories. So because it's completely open, people have made arms for it, drink holders, all kinds of things. So on the left is actually the turtlebot 1.5, and on the right is the turtlebot 2.0. And the biggest difference between these two is actually the base. So on the left is the iRobot Create, and on the right is a new platform that's actually much faster, better battery life, more hackable platform. So the 2.0 is pretty great. And of course, the whole thing is powered by ROS. It was developed at Willow Garage. And there's already quite a few Android apps for it. So if you go onto the Play Store right now and you search for ROS Robot, I think usually works quite well, you'll find quite a few ROS applications. So a sensor driver app will actually give or publish from your phone all the various sensor information that your phone already has on it. So the compass, the accelerometers, things like that. You don't actually have to do anything. It shows up as a node, and once you connect that node to your ROS graph, you can start taking advantage of it. The Robot Monitor is actually a diagnostic dashboard application. So if you happen to have one of these really fancy robots, and there's all sorts of different things that can go wrong, and you want to look and see if all the little green check marks are checked, you can do that on your phone. The teleop apps are, teleop is, or teleoperation is basically for remote controlling your robot, driving it forward and backwards, perhaps seeing from the video cameras on board, things like that, looking at the incoming sensor readings. There's several different versions of teleop available for different robots with different configurations. There's tools for building maps and navigating maps. And then there's more and more tools actually showing up for the PR2 itself. So the PR2 props, that's what they call when you can give the PR2 a high five or a fist bump, and you can control all that from your tablet. And then the pan tilt actually allows you to pan and tilt the head and see the world through the PR2's eyes. So if you want to see a little bit more about this, you can go to cloudrobotics.com. That actually takes you right now to the rosjava homepage. And ros.org, of course, is great as well. So any questions? Nope. OK. Oh, wait, there's one. Or that one.
Apps on some other devices that would contribute and in the cloud to build up information from robots. So if we are all walking around here, we will start drawing paths with our own devices, and then the robots could consume that information and the social robotic knowledge that they can exploit afterwards.
Okay, so it was a really long question, so I'll paraphrase for everybody. I'll do my best at least. So the question was, since this is about cloud robotics, this gentleman expected me to talk a bit about gathering information from lots of different existing sources and using that information to perhaps guide a robot or generate maps and things like that, right? So yes, this is definitely a great application. There was exactly one bullet that sort of mentioned this idea, which was information sharing. And I definitely think it's a very powerful concept. You could imagine robots in your home, some that are like the Roomba, is perfectly capable of vacuuming your floor, but is not capable of making pancakes. But at the same time, some robot that would be more capable, like for making pancakes, should certainly be able to communicate with that Roomba when it notices that the floor is dirty, right? It's a waste of the, you can look at this as distributing your resources more efficiently, because it would be a waste of time for the very complex robot that's making pancakes to actually go vacuum the floor when a much simpler, much cheaper robot could go do that itself. And then I think the other aspect of this is sort of like sensor network type stuff. And I think robots could definitely benefit from the existence of sensor networks that are connected to the cloud when that robot itself is also connected to the cloud. Great.
Do you know the Boeing project? Boeing.
Boeing, no, sorry.
At home?
SETI, sure.
Same principle.
Okay.
Would it not be a nice idea to have this kind of cloud computing, grid computing, in real time, and use this as a source for robots?
Okay, so the question is, would it be a good idea to use something like SETI at home as the cloud for doing this sort of robotics computation? I believe, yes, it could be. I think in many cases, these sorts of grid computing things have very high latencies and very high unpredictability about what kind of compute resources are available. So it pretty much depends. But for something like gripping, when you want to figure out how am I going to pick up this coffee cup, right? This is something that can be run offline in simulation across lots and lots of cores. And in that case, this is a pretty great use case for that, right? Because all we want to be able to do, well, there's lots and lots of compute time that goes into figuring out how to approach this problem. But then when we want to actually solve it, there's very little compute time. So if you solve the problem, if you find a great solution on this SETI at home type network, then you can save that and retrieve that from the cloud on the robot at the time you need it. Yeah. Anybody else? So I'll be here. Feel free to come up if you're too shy to shout something out right now. Okay, thanks very much.